Okay, thank you everyone for joining this webinar. I'm really excited to present Dr. Aaron Kochelik. He is an assistant professor in the School of Physical and Health Education. Prior to that, he worked as an ergonomics research associate at the University of Saskatchewan. His doctoral research evaluated tendon motion and shear in the development of carpal tunnel syndrome. So Dr. Kochelik has a lot of experience and knowledge around carpal tunnel syndrome, and he will be presenting to us exploring the traditional and alternative ergonomic assessment methods to predict injury risk of work-related carpal tunnel syndrome, evidence from the lab to practice in the field. So thank you, Dr. Kochelik. I will mute my mic and then you can present, and at the very end I will open it up to questions. People can type in their questions in the chat box. I will read them to Dr. Kochelik and then he will respond. Thank you.
Greetings everybody. Thanks for following along today, particularly so close to the Christmas break, and greetings from North Bay, Ontario, where we are now in day 3 of a snowstorm. So hopefully we'll be passing along some of that snow to other areas of the country that are looking a little more greener. Today my plan is to talk about traditional ergonomic assessment methods. So I'll start with a discussion around the most common methods that are used to assess injury risk of the upper limb. And I'll focus a little bit on my doctoral research, which really looked at mechanisms of carpal tunnel syndrome and ways to use that information to look at alternative ways of assessing risk. And then I'll spend the last bit of the talk talking about how I'm applying this, or will be applying this, in a ongoing field-based study out of Saskatchewan. So hopefully you find one or more of the areas of the talk useful today. So just as a starting point, Dempsey and colleagues in 2005 conducted a survey of 308 professional ergonomists, and they focused on the physical tools used to measure physical exposures, as well as the risk assessment methods that they use once they've measured those exposures to identify risk of the upper limb. And they identified or asked questions about 3 observational upper limb assessment methods, which were the rapid upper limb assessment, the strain index, and the hand activity level method. And although they asked quite a few questions, and as well as not just whether it was used or not used, but asked about how frequently they've used, I've focused on just whether this was a tool that was indeed in the professional ergonomist toolbox. So was it something they had used in the past? So of those methods, 51.6% identified using the rapid upper limb assessment method, or RULA. Slightly few identified using the strain index, and 22% identified using the hand activity level. So and I'll just also mention that the concise exposure index, or OCRA, didn't actually register on this assessment of physical methods used. So if anyone's actually used that method, I'm always interested to hear your experience with it. It doesn't get used too often just because of how difficult it is to use. And maybe just to kind of compare and contrast that with probably our most widely known method for assessing injury risk, the Nash lifting equation, 83% of ergonomists identified having used that tool before. So slightly lower percentages for upper limb tools, but that's not surprising. Upper limb musculoskeletal disorders are not quite as prevalent as disorders of the low back, although we know that they can be more expensive to repair and rehabilitate. And the reason that most ergonomists identified using these methods was primarily due to ease of use, but also suitability of the method. So it's good that ergonomists think that they're using the right method for the job. So I'll just kind of start with a brief kind of overview of these common methods, and I'll also introduce the revised strain index, which as of this year has been updated in order to reflect some new realities in assessing risk. So the rapid upper limb assessment method was developed by McKechnie and Corlett in 1993. It's really designed to be a quick screening tool for investigating work-related disorders of the upper limb. So it's quite a broad tool. And it was based on previous posture classification systems, the OS system, in order to sort of identify risk based on posture. So if I can sort of draw your attention to that first picture on the left of the screen, you can see that what they did is they sort of classified or scored risk based on what posture you were in. So for shoulder flexion or extension, if you're in between 20 degrees of flexion extension, you get a relatively low score of 1, whereas if you're at a fairly high flex posture of over 90 degrees, you get a higher score of 4. And they also had these score adjustments. So for instance, if you had a shoulder abduction, you'd also add 1. So at the end of the day, you get a score for the shoulder, and then you kind of continue on through the elbow, the wrist, as well as wrist twist, or what they mean by that is forearm pronation, supination. In addition to assessing just the upper limb, they also classified postures of the axilla. So, for instance, for neck flexion extension, they had a classification system where you could see neck extension being the worst, you're getting you a score of 4. So that existed for the neck, for the trunk, and then they also scored legs in terms of whether they were supported or not. So what these scores would do is then kind of fit into this larger scoring table. So for the upper limb, for instance, if you had a score of 1 for the shoulder, you would kind of tick that off and you'd work your way through. So you'd register your score for the lower arm, which is the elbow, the wrist posture, as well as forearm pronation supination. And that would give you a score of somewhere between 1, showing that this posture is relatively neutral for the upper limb, or the worst that register on this chart would be a 9. In addition to just scoring postures, they also introduced a muscle force score with a score ranging from 0 to 1. And what they asked about specifically here was whether you were doing a static exertion or doing exertion frequently. I believe they set a frequent exertion as 4 efforts per minute. You then added your final score, which is your force score or load score, and this would represent the force that you're actually applying at your hand, so any external loads in terms of the kilogram weight. So at the end of this, you get one final score for the upper limbs, and then you'd also repeat that for the neck, trunk, and leg posture and get 2 kind of scores, one representing sort of each part. These scores would then fit into the grand score, which I've sort of highlighted here on the right, and scores could then, once you sort of sum these 2 tables together in a new table, you could get a score of anywhere from 1 to 7, which would identify what the risk was of that job. So 1 to 2, for instance, would mean no action was required and it was a safe job, whereas level of 7 would put you in that level 4 category, and it would say investigate and change immediately. You can kind of see from the language that this was meant to be an evaluation or a screening tool in order to identify where risk may exist in order to do a further evaluation. So the language is sort of reflected in that grant score. As well, hopefully it was evident that RULA was really a posture-based model, right? The scores that could increase that grand score the most were really based on posture, whereas forces or frequencies had a much, or repetition had a much lower component on that final score. This is sort of important because at least for the wrist and hand, or for the distal upper limb, the most recent evidence really suggests that wrist posture or hand posture may not be an independent risk factor for musculoskeletal disorders of the upper limb. So it's good that it was, in a sense, that it was a broad tool, but if you're looking to categorize injury risk for the distal upper limb, you might be missing something there using this tool. In addition, because this tool used a static sort of approach in terms of getting a static picture to base your postures on, posture sampling is a large part of it, so you have to choose one image to assess. And they suggested sometimes using the most frequent or the posture that had the highest load, and not surprisingly, there's research out there that shows that based on what you choose, this can drastically influence your score. So I'll just point out that probably the hardest part of doing a RULA is sort of tracking through the different steps in terms of scoring the tool. And actually, an ergonomics group at Cornell University has done a really nice job of moving this tool into a spreadsheet, so right into Excel, where you can put your scores in and it actually sums it for you. So I've posted the link there on the bottom of this page, and I will share my slides, and it's sort of a fun tool or a fun way of getting familiar with the tool if you're looking to learn more about it. So shortly after RULA, Moore and Garg in 1995 actually developed the strain index, which really had a greater focus on musculoskeletal disorders for the distal upper limb. Within this tool, they identified 6 different task variables to assess. This included intensity of exertion, or how forceful the task was, the duty cycle, the frequency in terms of efforts per minute, as well as the worst wrist or hand posture within that task, the speed of work, and the duration per day. So for each of these 6 task variables, what they actually did is separated them into 5 different categories. So for example, for intensity of exertion, there would be a light category as the first bin or category, and all the way to the other side, the 5th one would represent a very forceful task. And so you would assess each of these task variables, sort of classifying them into one of these 5 bins, which would then give you a multiplier for each task variable. And then you'd multiply all these together to get a final score. So the strain index scores below 3 were considered safe, whereas strain index scores above 7 were considered hazardous. So I just thought I'd maybe overview a little bit how we could actually measure some of these task variables that would go into the strain index. So for intensity of exertion, for example, we could use EMG to actually get an idea of what the muscle force was. So use muscle activity as a proxy to determine how forceful the task was. This is an approach that academics certainly like to use, but of course EMG systems are quite expensive and probably not often available to professional ergonomists in the field. Another approach could be to use a Mark 10 force gauge to actually measure what the force of that exertion was. So for example, if it's a finger pull, you could measure what the force of that finger pull was. And then you could actually sort of compare it to strength data, such as Dr. Potvin's hand pack, to get an idea as a percentage of how difficult that task was. So you can get an idea of the intensity of the exertion in that way. As well, Moore and Garg suggested using just a ratings of perceived exertion scale. And I would imagine this is what happens most often. It would be a 10-point scale where you ask the worker how exertive or forceful a task is, and they would give you indication on this scale, with 0 registering as no exertion at all, and 10 being that they're working near their max. So there's different ways you can get at getting this intensity of exertion. And although the RPE scale might be a little more prone to error in terms of asking or relying on an answer from the worker themselves, it's been shown to be a reliable tool to use. In terms of quantifying some of the other task variables, duration per exertion, the efforts per minute, and duration of task per day are all basically related to the timing of a cycle. So you can actually get these fairly easily by just having a stopwatch and timing some important events that are happening throughout that work cycle. Wrist and hand posture can be assessed with some more complicated tools, such as electrogoniometers or even these data clubs, which contain several electrogoniometers in them. But I would imagine most often what happens is it's really the eyeballometry test. You actually just look at the worker as they're working and assess what that worst posture is in terms of sort of an assessment on the spot. So all these are good ways to do it. Depending on what you have in terms of equipment, that will obviously determine how you go about collecting some of this data. So I just thought I'd now like to point out that as of actually just this year, in 2016, the strain index is now antiquated. Garg and colleagues developed a revised strain index, and as you can see from their title, they believe it's an improved upper extremity exposure assessment model for assessing risk of the distal upper limb. So I thought I'd talk about just how it differs from the original 1995 strain index. First, they've omitted the speed of work task variable. They felt that it was already kind of considered in other variables that are in the model, such as efforts per minute or the duration per exertion. They've exchanged the duty cycle with duration per exertion. It's a relatively small change. And perhaps most importantly, or their largest change, is that all of these task variables are now assessed continuously instead of just being binned into one of 5 possible categories. So they believe this actually creates greater discrimination when you're assessing risk using the revised strain index. So I thought I'd just demonstrate what I mean by this in terms of this now continuous assessment. So I've plotted the first task variable in the strain index here, intensity of exertion. And the green line here shows the actual bins or categories that intensity of exertion was assessed in those 5 different categories. So on the horizontal axis here, I've plotted intensity of exertion as a percentage of max that a worker could work. You could also think of this as the Borg scale. If you could supplement this exactly with the Borg scale, instead of it being 0 to 100, it would be 0 to 10 here on the horizontal axis. And on the vertical, this shows the multiplier, the score that you would get for this task variable. So you can see in the first bin, if you're working less than 10% of your max, you're doing relatively light work in terms of the force requirements, and then you would actually get a very low multiplier score of just 1. Whereas if you're working very forcefully or near maximum, above 80% of max, you would have been in that 5th sort of category, and you get a much higher multiplier, showing a higher risk for this job and a score of 13. What the revised strain index does is actually takes these categories and makes it sort of one continuous line that you can assess anywhere on that line. So based on this equation that I'm showing up here, we would plug the intensity in from 0 to 1. So in this way, you get more discrimination. Instead of being stuck in one bin, you could assess what the multiplier would be anywhere on the line. You can see for the most part it follows fairly closely the original bins set by the 95 model, but it actually goes a little bit higher, so you get a bit of a larger multiplier near the end range here. I think what Garg and colleagues realize is that the math might scare some people away, and there's certainly some other methods out there that are a little heavier on math and they don't get used as much. So what they've also done is provided these nice tables in order to actually determine the multiplier using the tables instead of actually using the equations. So for example, if you're working at 10% of your maximal effort, or you registered a Borg scale of 0.5, it actually gives you the multiplier in the table. And they've actually provided these tables for each of the 5 different task variables in their model. So you could actually assess the strain index just using these tables, and it would still give you more in terms of discrimination because there's not just 5 bins, but several different multipliers that you can choose from. I just thought I'd point out one other one here that really changed quite a bit in the revised strain index in 2016. So I plotted the repetition or the frequency in terms of efforts per minute on the horizontal axes, and again shown the multiplier. And the green line here again shows the 1995 strain index. So you can see that the levels here are all sort of bunching up below 20 efforts per minute and doesn't change too much from level to level. In the revised strain index, they actually put a much greater effort on the repetition or the frequency aspect of the task. So you see that line goes up quite a bit higher, quite a bit quicker, giving a higher multiplier. And they also thought it was very important to provide additional comment or additional ability to assess higher than 20 efforts per minute. So a lot of jobs for the upper limb really took you above 20 efforts per minute, and it just sort of flatlined there in the 95 index. So now this actually provides greater guidance for these higher frequency tasks. And I've pulled this right out of their new 2016 paper. So this is looking at jobs that were originally assessed with the 1995 strain index. You can see scores ranging from 3.25 all the way to 13.5. And then what they've also done is shown what their new score would be using the revised strain index. What I'd sort of point out here is a little bit of this waterfall shape. So we're actually seeing that the range for the revised strain index is much greater. So there's greater discrimination or greater sensitivity now in the tool than previously existed for the 1995 strain index. So I think this is an important point, and certainly I think now the ability to sort of discriminate between hazardous and non-hazardous has been much better improved based on this revision, especially with the addition or the greater emphasis on the repetitive aspects in the revised strain index. I also thought I'd put one slide in here. This one didn't register quite as much in that original survey by Dempsey and colleagues, but it did register at 22%. So 22% of ergonomists identified using the hand activity level tool. So I thought I'd just point out that if you've actually done a strain index, you really have all the information you need to also perform the threshold limit value for hand activity level. So in terms of normalized peak force, you've already actually looked at the intensity of exertion in the strain index, and the hand activity level you can actually get based on the duty cycle and the frequency of the task. So you've already actually collected all the information you need if you're doing a strain index to also use this tool as well too. And if you get a value that is above this sort of threshold limit value line, this would represent a significantly elevated risk for MSDs. One thing that I will point out with this tool is that it put a greater emphasis on the wrist and hand. So it was really focused on monotonous, highly repetitive tasks for the wrist and hand, and not the entire distal upper limbs. A little bit more specific yet. So I think what's really interesting or important to me is that each method really weights risk factors quite differently, right? And not surprisingly, if you're sort of assessing or taking into account these risk factors differently, they can lead to widely discrepant results if you're using each tool. So for example, the RULA tool puts a much heavier emphasis on posture compared to force and repetition. Whereas the strain index, or the original strain index in 1995, was heavily dependent on the force, much more dependent on the force than any other risk factor. So if you had a high force, most likely this tool is going to show you that you're in a hazardous range. The threshold limit value for hand activity level put roughly an equal emphasis on force and repetition, and posture didn't even really register, right? You were only supposed to really consider posture by taking into account if this would affect the forceful kind of aspect of the task. So if you're doing a pinch grip, for instance, versus a power grip, that's going to sort of use up more of your maximal force stores, so you would take into account in that way. I'll also point out that the revised strain index in 2016 actually sort of starts to match much better the threshold limit value for HAL in terms of what risk factors are the most important. So they put a much heavier emphasis on the repetitive aspect, and so now these are sort of closer, more on level footing. My thesis, which was performed prior to this revised strain index, really looked at these three different methods and said, geez, it's amazing how different they will give you in terms of risk scores. So my thesis really focused on what if we took a more mechanistic approach to looking at ergonomic risk assessment for the wrist and the hand. This is research I did at McMaster University under supervision of Dr. Peter Keir. And so the next portion of my talk will really focus a little bit more on this sort of different view or way of looking at assessing risk. So if I'm going to take a mechanistic approach or look at the actual injury mechanisms that cause carpal tunnel syndrome, I have to know a little bit about anatomy, so I'll just spend a minute here kind of overviewing some important anatomy of the wrist. So the carpal tunnel, I'll just sort of trace it for you right here, is formed dorsally by the carpal bones, And then palmarly, it's sort of the roof of it is sort of formed by this transverse carpal ligament. Passing through the carpal tunnel are 9 different flexor tendons, 2 to each finger and 1 to the thumb. You can also see the median nerve, which is that yellow structure sort of nestled in the radial corner of the carpal tunnel. Now this whole space is about the size of a dime. So that's a very small space for the number of structures that are passing through it. So not surprisingly, one of the injury mechanisms that we see that sort of shows up over and over again seems to be this sort of idea of a sliding injury. If you look at how many tendons are jam-packed in that area, they'd be sliding back and forth depending on the finger movement you're doing. That starts to make a little bit of sense. So I thought let's take a little bit of a closer look here at what tendon gliding looks like in the carpal tunnel. In the carpal tunnel, tendon gliding is actually quite unique. There's a two synovial line bursae, which enwrap the tendons, but there's also this extra synovial gliding mechanism, which is histologically similar to paratenon. Now, in most joints or most areas of the body, you'll have one or the other, but not necessarily both. So this is quite unique. This extra synovial mechanism in the carpal tunnel is called the subsynovial connective tissue, or the SSCT. Because that's such a mouthful, you'll hear me say SSCT quite a bit. So I'm going to shorten this sort of tendon gliding mechanism to SSCT. And what it's basically created by is several layers of collagen, which are linked together by small perpendicular fibrils. So I think the best way to sort of highlight this mechanism is to show you a video here of what this looks like. So this video, just to sort of introduce you to it before I start to play it, shows actually a tendon release surgery by a French surgeon at 40 times magnification. So across the screen, what we're actually seeing is the tendon, and then surrounding the tendon is this specialized tendon sheath, or the SSCT. You can see it's a highly vascularized structure. And as I start to play this video and you see the tendon slide, what I'd like you to pay extra close attention to is how the different vessels in each layer of that structure, the SSCT, move relative to each other. So as the tendon starts to move to the right, we can see that blood vessel 3 actually overtakes blood vessel 2, and just near the end, both 3 and 2 get sort of closed in on by blood vessel 1. So these are actually blood vessels in different layers of the SSCT, or the different layers of the specialized tendon sheath. What's particularly interesting here in this video is we see that there's a continuity between these layers. So that's particularly important because during tendon displacement, this specialized sheath, this SSCT, is strained, such that layers deep or closest to the tendon move first, and then layers further away or closer to the periphery move second. And this is what gives this effect of seeing different blood vessels pop up or move past each other at different times. These are vessels in different sheaths, and they're moving depending on what area they are, deep or superficial in the SSCT. This is particularly important because in carpal tunnel syndrome, the most common physiology we find is actually fibrosis or thickening and hardening of this structure of the SSCT. We also see that the thickness increases with the severity of the symptoms. So when we actually look at where the damage is, closest to the sort of right next to or adjacent to the tendon, this again sort of shows us that tendon sliding or tendon shear seems to be a really important part of the injury mechanism in terms of the injury cascade that eventually would lead to the development of carpal tunnel syndrome. So that sort of brings me to the purpose of what my doctoral work was, which was really to quantify tendon motion, tendon shear, since I thought these related quite importantly in the injury process of carpal tunnel syndrome, and to look how they would be influenced by our well-established physical risk factors that show up in these ergonomic risk assessment methods. So for example, awkward postures, which plays an important part in RULA, forceful exertions, which is extremely important in the strain index, and speed of work, which obviously factors in all of them, but it's on a relatively even footing in the TLV for Howe with forceful exertions. So I thought, can we actually use what we think is sort of part of the injury process to quantify these variables and start to get an idea of how these risk factors maybe should be weighted if we're going to assess carpal tunnel syndrome risk. So I'll just sort of highlight some of the methods I use without going into too much detail. Ultrasound was a big part of my thesis because it allowed us to look internally at how the tendons were moving relative to each other. So I can draw your attention to the video on the right. You can actually see two tendons sliding back and forth here in the screen that I'm just sort of pointing out with my mouse here. And just to the right would be the carpal tunnel. So we're just sort of scanning just proximal to the carpal tunnel. You can see the tendons have this sort of speckled pattern or this spotted pattern. And on each side of a tendon, you see this sort of bright layer. And what that bright layer is it's actually the subsynovial connective tissue, that specialized tendon sheath that surrounds each tendon. So we can actually use ultrasound or diagnostic imaging to assess both the tendon and that sheath at the same time in terms of how they're moving relative to each other. What I actually did with that data is I actually developed equations that would allow me to predict what the displacement of the tendon and that surrounding sheath would be as a function of joint motion. So this first graph on the right here shows what the tendon displacement would be, and these are these solid lines here, and the subsynovial connective tissue displacement would be, these are these dashed lines here just underneath it, as a function of metacarpal phalangeal joint motion. I also did the same just to the right for proximal interphalangeal joint motion. And particularly important for me is you can see that these lines are sort of bunching up, right? Displacements for the tendon are quite a bit higher than displacements for that surrounding tendon sheath. So what that's showing is that there's relative motion or potential for shear between these two structures. And all the different colors represent is just different size of wrists. So the blue line, for example, would represent 95th percentile anthropometrics, or 95th percentile size wrist. And not surprisingly, if you have a larger sort of joint, then you're going to have greater motion there. But I was quite happy with the results of this from ultrasound, being able to differentiate between the tendon and that surrounding sheath, and then have some equations that could actually predict how they move relative to each other. So I could start to use these to get an idea of the shear between the two structures. So before I move on to the next part, I just thought I'd mention that the next slide will show cadaveric material. Now, this is something that you might not be overly comfortable with. I completely understand that, and just thought I'd give you the chance now to sort of maybe kind of get up and sort of, move your legs around and maybe miss that slide if it's something you think might bother you. Just turn that down a little bit. So next, ultrasound was a very good way to start to look at different motions or different or potential for shear between two structures. But we thought, is there a way we could do this a little bit more directly, right? So ultrasound sort of looks at the motion but doesn't actually measure the friction of what those tendons are doing. So for this, we actually used the cadaveric approach, where we dissected both proximal and distal to the carpal tunnel, and then we actually measured the friction through the carpal tunnel. So you can see these small lightweight force transducers on each side of the carpal tunnel, which would allow us to actually start measuring friction as the tendon's being moved via a motor. So just to sort of highlight a little bit of data from this study, this whole graph shows friction through the carpal tunnel for that one tendon in a neutral wrist posture. So the different colors here represent moving the tendon at different speeds. So this would be getting at the repetitive aspect of movement frequency. So a higher tendon velocity would be representative of a higher, more frequent task. And then you can see we also tested 3 tendon forces, so getting the idea that if you're doing a task that's more forceful, that's going to create more force internally in your muscles and tendons. So we kind of replicated or simulated different forces in that way. And again, these are all kind of frictional measurements for a neutral wrist posture. So sort of in our low velocity, low force task, all the way up to our high velocity, high force task, we saw an increase in friction of 33.5%. If I then just compare and contrast that with what happened in a flex wrist posture, so again starting to manipulate another risk factor in terms of awkward postures, we saw a much higher or steeper increase from that low velocity, low force condition to the high velocity, high force condition. So it actually increased by 93%. So we're actually showing here is a multiplicative effect between tendon force and wrist posture. So when we're in a flex wrist posture, the effective force is having a much larger effect on our frictional measurement, which again I feel or we believe is important in the process of development of carpal tunnel syndrome. So this is a pretty important result, and certainly would reflect sort of the multiplicative nature of the strain index in terms of multiplying the different multipliers out. We're starting to see a multiplicative effect between 2 risk factors here. So what I actually did with this data is I actually developed sort of a conceptual model that will allow me to predict not only relative motion between the tendon and that specialized sheath, but also measure tendon frictional work, with the idea that we'd be building on traditional ergonomic assessment methods that just looked at tendon travel. So not only would I be just looking at how much tendons are moving, which has been done by some researchers before to look at different workplace interventions, but I'd actually be looking at what is the friction of that tendon as it's moving. So for my first series of equations used in my ultrasound, I could actually determine what the tendon displacement is as a function of joint motion. And if I know what the tendon displacement is, I can then predict my gliding resistance or the friction of that tendon. And then sort of like the strain index or other tools like Nyhaus-Lipton equation, they're multiplicative. What I could then do is start to take into account other risk factors that may further increase the friction or risk of injury for the carpal tunnel. So for example, if I'm working in a job that has a high force component as well as in a flex wrist posture, this would give me a factor above 1, and it would increase my original frictional score even higher, representing that additional friction that would exist for a high force job when posture is in a flexed or non-neutral posture. And I could do the same thing for tendon velocity or highly repetitive movements. If you're working a highly repetitive job, this would also again increase the risk factor above 1, so it would further increase the risk. So in this way, I've created a conceptual model that actually weights the risk factors based on sort of the underlying mechanism of injury for the carpal tunnel or carpal tunnel syndrome, which is related to tendon shear or tendon friction. So I just thought I'd point out how my model sort of compared to a traditional study, one done by Silverstein and colleagues in 1987, that sort of measured physical exposures in several jobs in the workplace and classified them based on those physical exposures. So that first white bar there on the far right of this first graph labeled A represented a job that had a low force and had a very low repetitive aspect to it. And you can see in terms of who got injured, they've just normalized all that data to this low force, low repetitive job. If I then compared that to a job that has high forces but still has a relatively low repetition, you can see that it increased slightly, but not drastically. So just that one increase in that one risk factor alone did result in a greater increase in people getting injured or people getting carpal tunnel syndrome, but it wasn't a drastic increase. If we looked at jobs that had a highly repetitive component but a low force component, we saw that high repetition alone actually increased the risk of carpal tunnel syndrome greater compared to a job that was just forceful on its own. And then if we had a job that had both a high force and a high repetition, we saw a very drastic or multiplicative effect of increased risk in terms of the odds ratios. So more than 8 times the people would get injured if they're doing a high force, high repetitive job versus a low force, low repetition job. And if I sort of highlight what that odds ratio data from this sort of classical study looks like compared to the frictional measurements I would get with my model. So this first one is based on a model I've created on my ultrasound data alone. And the second one is a little bit more detailed, including greater frictional estimates from the cadaveric work. You can see that the bars are actually mimicking each other quite well in terms of capturing that multiplicative risk. So in terms of sort of high force not being as important of a risk factor quite as high repetition, but if you have both high force, high repetition, a greater increase in friction based on that compared to the low-low. So overall, my models are actually reflecting what the injury data shows fairly well, and I would argue probably better than any other tool that existed until the revised strain index came along and they actually put a much higher emphasis on repetition. So I actually think that now with that change, they're going to come much further into line with what the odds ratio or the injury data looks like. So for the last part of the talk, I thought I'd highlight a study that I've had the pleasure to be a part of under the supervision or under sort of the investigation as the primary investigator of Dr. Catherine Trask out of the University of Saskatchewan. So as I was passing through as a research associate, I was out there for about 2 years. I was lucky to get involved in this study, and it actually provided an opportunity to continue working on some of the my own interests in relation to wrist and hand injuries. So this is a project funded by the Workers' Compensation Board in Manitoba. It's a relatively large study, again headed by Dr. Catherine Trask at the University of Saskatchewan, and it's a 6-figure project, so it is a relatively large piece with many moving different components. So just as a little bit of background into this project, within the past few decades, and particularly since the Great Economic Recession, we've seen a rapid intensification in pork production within Canada. This has led to large-scale modernized production systems, and when you start to move work into these sort of large-scale production systems, what you see is greater specialty work or greater specialization in the jobs that exist. When you get this sort of greater specialization in jobs, this often necessitates different technological advancements in order to sort of keep up with the changes in the processes. So one of these technological advancements in pork production was actually the needle-free injector, which was used to deliver medications such as vaccines, or medications to sick animals. And the idea here is that they would eliminate broken needles, which could contaminate a whole shipment of meat if that were to happen and go unreported, or would also prevent needle stick injuries in workers. So if you have a needle in one of these injectors, there's always the chance that you sort of lose focus for a minute and actually sort of inject yourself with medication that was intended for a pig and not for yourself. So this sort of technology would eliminate that. Often what happens with ergonomic sort of redesigns or changes or interventions is that these interventions happen, but not without a whole lot of necessarily assessment in terms of what that change will do. So there's some obvious benefits here in terms of what a needle-free injector would do, but our argument was that there needs to be a bit more of a complete process that should be involved in sort of assessing what the net benefit is for using a new technology like this. So just before I sort of give you an overview of the project, I just thought I'd show you a very quick video to show you what this needle-free injector looks like. And what it actually is doing is actually just forcing the medication directly through the skin of the pig using forced air and eliminating the needle. So you just have to obviously make sure that you have relatively good pressure with the animal, and then the actual pressure of the jet stream would actually force the medication in. So in terms of the study overview, what the plan was to develop a decision model, a cost-benefit model that would look at the overall sort of net benefit of implementing a new technology. And we really used this needleless or needle-free injector as a test case to develop this larger model that could be applied more broadly, actually. So the inputs into this cost-benefit model were implementation, or will be, this is an ongoing project I should mention, with some phases done and others still ongoing. Implementation costs, so what does it actually cost to implement a new technology such as the needle-free injector. Injury rate data, so looking at barns that have already made the change and seen if there's been any difference pre-post in terms of injury claims. Exposure assessment, and this is where I'll focus my energy on today because my talk so far has really been about physical exposures and how they're used to quantify injury risk. So I'll talk a little bit more about this in a minute. We also looked at, or are looking at, worker perceptions and organizational factors, as well as overall productivity that comes with this implementation change. So to focus a little bit more on exposure assessment, this part of the project, actually, we've just wrapped up data collection and are just getting into the processing a little bit now. So I'll just sort of highlight how this data collection went a little bit. So we actually quantified physical exposures for both a conventional needle injector and a needle-free injector at the Prairie Swine Center, which is a pork producer just outside of Saskatoon. And it also functions as a large hub for research in this area. So we were lucky to have the Prairie Swine Center as a research partner on this grant and be able to gain access and able to actually look at implementing this needle-free injector here at the Prairie Swine Center. So how do we quantify physical exposures? Well, we use surface electromyography. We use 4 channels here of EMG to represent the wrist flexors and extensors for both the left and right arm, as well as we actually use a cyber glove, which is a sort of this spandex or lycra fitting glove that would form to your hand. And it actually has 18 embedded electrogoniometers into it, which would allow us to get an idea of postures of the hand. So we're measuring posture, as well as, because we have a whole time history of the posture, we get an idea of the motions or the repetitive aspects of the task, and we are also measuring EMG to get an idea of the forceful aspects of different injection methods that we're testing. So I just thought I'd highlight the research team. This is a project. The data collection part has just wrapped up. You can see Dr. Trask there on the left, and I'll maybe highlight the 2 students here that probably did the majority of the data collection work, Benga Adebayo and Zhao Qi Zheng, who were really probably stuck doing all the data collection part of this project. So special thanks to them who really did the bulk of the work in this data collection. As well as just highlight the other members here of our team who are actually members of the Prairie Swine Center and were integral part to actually making sure that we did this in a way that was kind of, worked well with the employees at the Prairie Swine Center in terms of implementing new technology. So in terms of experimental testing, our data collection is sort of wrapped up. We actually collected 684 injections in total, 378 of those with a conventional needle injector and 306 with a needle-free model. These tasks were performed in 2 different sort of these injections were performed in two different subtasks. The first was piglet processing, which is a bit of a larger process, involves things like clipping tails, clipping teeth, and that sort of thing. So it's not just there's not just a vaccination process there in terms of medication delivery. That's part of it. It's a bit of a larger process. You can see we collected data for 3 workers there and 324 injections. And then for vaccinating weanlings, we also collected data on 3 workers there and 360 injections. And this part of the job would be much more specialized in terms of just providing a vaccination and moving on to the next piglet. So a little bit more focused on just the injection part of the task. The overall design, or the design we envisioned, was that we would sort of collect data on one worker using EMG in that data glove. We'd also capture video to look at sort of productivity analysis. And we'd ask them to do several crates. Each crate would contain several piglets, a whole litter of piglets. And you can see we would use the needle injector in that first crate. They'd sort of move through several crates using that one technology, the conventional needle injector. And then they would flip over and use the needle-free injector for the next 5 crates to sort of match how many injections they were doing with each technology. So sort of a repeated measures design here. In actuality, at any one given time, there wasn't enough piglets to sort of do it in this way. So often what we had to do is we would capture all the needle injections in one day, come back, measure that same worker, and capture the needle-free injections on the second day. So I just thought I'd highlight how my tools that I developed in my PhD thesis could be used to start to look at injury risk here, or sort of assess these different injection methods in terms of assessing the intervention here. So I should mention that this is only based on a few cycles. The data collection just wrapped up, and this is really preliminary, very preliminary data analysis, just to show more how the tools could be used as opposed to get a final idea of what the results here. But you'll get an idea of what we're working towards, or what I'm working towards on this piece. So what I did here is I actually used my equations from ultrasound to predict what the overall travel of the tendon would be and the adjacent subsynovial connective tissue would be for an average cycle. So I have sort of bars in 2 groups here. These are bars for the needle injector, conventional needle injection method, and then bars here for the needle-free injection method, so the new technology. And so if I just could draw your attention to the black bars, this would be the cumulative travel of the tendon for an average cycle. And as you can see, for the needle injector, the conventional method, there was slightly greater tendon travel as predicted by my model compared to the needle-free injector. So this might imply a little bit more potential for shear based on this one measure alone. I should mention that this idea of measuring tendon travel has been done in the past and is not in itself necessarily a new idea. But what my model added was this ability to also measure the cumulative travel of the surrounding tendon sheath. So that would be this line, right, or these bars right here that have this spotted pattern. And if I believe that the injury mechanism for carpal tunnel syndrome is related to tendon shear, then the relative motion between the tendon and tendon sheath would really give me a pretty good idea of the shear potential between these 2 structures. And if I start to actually look at this, you can see that the difference between the tendon and the tendon sheath for the conventional needle injector was actually quite a bit greater for this subset of data that I looked at compared to the needle-free injector. So this would actually imply an overall greater potential for a shearing injury in the development of carpal tunnel syndrome for the conventional needle injector. So what I then did is just plotted these to show them in a little bit more detail. So looking at what the displacement of the tendon is and subtracting the tendon sheath from that. So getting an idea of the relative displacement between these 2 structures, with the idea that this would be a good measure or proxy for the shear between these 2 structures. And I've sort of normalized that to the overall motion of the tendon for an average cycle here that I looked at. And you can see again that for the needle injector, the conventional method, we see a much higher number here, so much greater potential for shear injury compared to the needle-free injector. What I can also do is then use my further model and relationships I developed in my cadaveric work to actually even incorporate the other risk factors involved in this task. So in terms of the peak force determined by our EMG data, as well as the peak velocity determined from the velocities or the joint angles over time from the data glove. You can see they were mildly higher here for the conventional needle injector for the subset of data that I looked at. And that kind of made this differentiation even greater. So we're seeing an even greater greater potential for shear when we start to add in the effects that force and frequency or repetition would have on potential for shear between these two structures. So I'm pretty excited about this data. Again, it's just a subset of the data for now. We'll certainly be working through a much larger and complete data set, and I look forward to sort of presenting that whole data in the coming years. So I just thought at this point I'd highlight again that this is an ongoing project by Dr. Trask, and so this exposure assessment has just wrapped up now. We're just starting to work through data analysis, and we'll definitely be presenting this data at some of the coming ergonomics conferences over the next coming years. So keep an eye out for us. And then as a step for me, I recognize that my newer sort of methods, that sort of weight risk factors based on friction and shear, are still in a stage that might work well for researchers, but wouldn't really lend themselves well to a sort of a usable tool in the field. The equations are there, but it would certainly take some effort and some time on the part of an ergonomist to actually use those, and I do recognize that. So I just thought I'd point out that one of the next steps that I'm working towards is really developing an app that would start to use these relationships and develop a risk assessment method using these relationships from my doctoral thesis. So I'm just highlighting one app here that was developed. So this is a 3D SSPP app out of the Michigan group. So this is sort of a simplified model of their biomechanical model that's available. It's actually quite fun to play with. My ergonomics class always has fun when we get to take out our phones and actually start playing with some apps for biomechanical modeling. So my own goal is really to start to move my own tool into a method that would be much more accessible to a much wider audience. So also keep an eye out for that over the next coming years. I think with that, I think that's about all I had for today. I just want to thank all those that have had a very large impact sort of on my career path and where I am today. So that's always important to highlight again Dr. Peter Keir, who is my supervisor for this mechanistic work out of McMaster University, and Dr. Catherine Trask, who I spent 2 years out at the University of Saskatchewan and had a chance to work on this very fun project focused on wrist and hand injuries in the pork industry. With that, thank you for your time. And I think this is the part where we do questions. So I'll bring
Yes, thank you, Dr. Kochelik. That was very interesting. Very excited to see the app when it comes out. Right now we'll open it up for questions. So if anyone has questions, just type them into the chat box, and then I will read the question out to Dr. Kochelik. I'll mute my mic so that you can respond at that time. And we just have 10 minutes for questions about, so if anyone has questions, please go ahead and write, and maybe while I'm waiting for people to write their questions, I had one question. You mentioned that you had studied looking at the effect of posture when it was in wrist flexion, and I was wondering if you looked at the effect of posture in any other wrist posture.
We tried initially to do both 30 degrees wrist extension, 30, and then a neutral posture, and then 30 degrees wrist flexion. And we had a really tough time replicating or simulating an extended wrist posture correctly in a cadaveric model. It just, for everything we tried, the mechanics, what the wrist wanted to do was not very natural in an extended wrist posture, and so we had a really tough time replicating that. I would probably point out that I've really focused on tendon shear today as sort of a mechanism of injury, and it's obviously one of my favorites, being that I've devoted so much time in my own doctoral thesis to that. But it's not the only injury mechanism. So in wrist extension, for example, a much larger concern might actually be related to the carpal tunnel pressure. So if you're sort of holding a tray, if you're working as a waitress or a waiter and you're holding a tray all day in an extended posture, that would really increase carpal tunnel pressure. So it might be that in some of these other postures that I didn't test, friction might not be as large of a concern compared to wrist flexion. In flexion, the tendons sort of move palmarly and they kind of go right up against that transverse carpal ligament, so it creates a much larger potential for shear with the other structures around. But it's something that definitely moving forward, it would be nice to incorporate more data in terms of different postures. We saw that it had a much larger multiplicative effect with other risk factors when we even changed that wrist posture just a little bit.
Thank you. I guess one other question is, do you have any estimate of your timeline for when you might have your app available?
Well, in the first first semester of a brand new job as assistant professor here at Nipissing University in North Bay. So I haven't found a student with that sort of experience or background yet, but it's certainly high on my list in terms of seeking some funds that would allow me to develop an app and sort of getting the expertise around it. There actually is a few other researchers in this department with more of a focus on youth participation in sport, and they've created some really neat apps specifically focusing on Indigenous participation in sport. And so I definitely have a really good group around me to sort of pick their brains and how that processes went for them and where the expertise might be to assist on that. So it's really something I'm really very high on, but it's still in the early stages, I guess, in terms of a conceptual idea.
No worries. Didn't mean to put more pressure on you for that. So thank you for the presentation, and I heard you say during the presentation that you would make your presentation available. So what we can do is send a PDF out to the attendees, and as well we are putting the past presentation, as this presentation is recorded, we're putting the past ones on the website. If you go to the ACE website and you go under resources, you'll see there's a link to past webinars, and initially there's a page that lists all of our past webinars, and then you have to be logged in to access the next page, which has all of the webinars listed plus the actual link to the webinar. So that page, I don't think, not all of the links have been updated, so you'll see that we've had a lot of webinars actually over the last 2 to 3 years, and we probably only have maybe 8 of them linked, but we are in the process of doing that. So Dr. Cochella's webinar will be up for you guys to review again in the past. And Dr. Cochella, if you have updated information, of course you're always welcome to give another webinar, or if you wanted to put something out, let's say you did get people in your department involved and got the app out and you wanted it to be made available, please let us know. We can put something like that up on our blog, on the ACE website. And if anyone has questions, I can see that somebody is typing right now, and I've seen some other people say excellent work, thank you. I'll just wait till Paulo is finished typing to see if he has a question. Okay. I think we have a lot of people saying thank you, it was a great presentation. So I might just close it off there. If anyone does have questions, you can email the ACE office, and then we can get that question over to Dr. Cochella for him to answer later. So thank you guys for participating. Today's presentation was the last presentation of 2016, and we have quite a good lineup coming up for 2017, so we're hoping again to have at least 7 to 10 webinars per year. If anybody has ideas of either they want to present or they have ideas of who they think would be a good presenter, please contact us. And as well, if there's anybody who wants to be involved to assist with coordinating the webinars, please contact us. We're always looking for volunteers. So thank you to everyone, and Merry Christmas, and we'll see you in 2017.